you very much for the introduction and the invitation also. So as you can see here, today we'll present a work that as of today is still a preprint, but we are working on some referee comments to improve the paper in these weeks. So the paper is on learning Hamiltonians of constrained mechanical systems, and it is a joint work with Elena Celedoni, Andrea Leone, and Brynjulf Oren, and we all work at NTNU here in Trondheim, Norway. So my plan for the talk is to first introduce our approach, which is shared even in other works, but it is quite different in terms of notation. So I want to introduce especially the notation. Our approach to approximating dynamical systems and how we can see this problem as an inverse problem. Then we will move to learning Hamiltonians of unconstrained systems. And then there is the second half of the talk, which focuses on constrained Hamiltonian systems, where we start with introducing a mathematical characterization of constrained Hamiltonian systems, since they can be described in many different ways. And then I will move to our approach on learning Hamiltonians of these constrained systems. So first of all, I want to start with the definition of the problem. And here I won't focus on just the class of Hamiltonian vector fields and dynamical systems.
No, I mean,
but, sorry? Oh, okay.
Just participants.
Okay. Okay. I forgot to say it, but if you have questions, just ask whenever you prefer. For me, it's fine. So I will start not directly on Hamiltonian systems, but presenting the learning framework for a generic vector field F, so a generic dynamical system. And here we will work on vector fields on Euclidean spaces, Rm. So suppose to have an unknown vector field, an unknown dynamical system, which is described by first order or ordinary differential equation like this one. And you don't know anything about the pointwise values of this vector field, but what you know, you have access to some indirect measurements of this dynamical system. And in particular, you have access to a set of trajectory segments, a set of snapshots of your dynamical system. And here we will suppose them to be uniform in time, these snapshots. So suppose to be interested in the dynamics on a certain subset of Rm, let's call it omega, and to have a set of n initial conditions, which are these xi's that belong to omega. For each of these, you have m snapshots of the updated dynamics. So Yij in the notation that we use is the updated position at time j times delta t, where delta t is a fixed time interval. And phi, big phi, will always be the exact flow map of the vector field F. So this is the position where you will be at time j delta t if at time 0 you are in position xi. And if you're dealing with real applications, then you have to take into account also some noise contribution to these trajectories. And these are these delta ij. So the goal is, supposing to have sufficiently many of these trajectory segments and them to be quite well distributed in omega to get a good understanding of the dynamics, you want to approximate the vector field on the wall of omega. So you want to extrapolate from this training set information about the dynamics on the wall omega. So the way in which you can do that is, first of all, introducing a parametric model. So introducing an auxiliary vector field, which is this f hat of theta. And this auxiliary vector field has a parametric dependency on theta. Theta can be a set of weights, which are like matrices or vectors, as usually in approximation problems. And this parametric model has the purpose of being trained so that it will match ideally the vector field we are interested in. And the way in which we want to train to optimize these parameters theta is by matching the trajectories of this auxiliary vector field with the training ones that we have. Indeed, what I want to stress here is that the way in which we can think to this problem is like an inverse problem. Indeed, we don't have pointwise values of f, and which is the function we want to approximate, but we just have indirect measurements of this vector valued function, which are the trajectories. And from these, we want to reconstruct the vector field we are interested in. So this is why we can think to this as an inverse problem. So with this parametric model, what we can do is, since we are just having access to trajectory segments, we want to get something to compare with those trajectories. So we introduce any numerical integrator, any numerical approximation of the solution of this ODE. So like explicit Euler, the simplest one, but one can use symplectic methods or any other numerical integrator in principle. And we want to approximate the trajectories of these at exactly the same time instance to which, for which we know something about the dynamical system, which is this one, given by the vector field f. So delta t, 2 times delta t up to m times delta t, where delta t is given. So these trajectories, these snapshots will be denoted with an hat. So yi j plus 1 hat is the updated position after a time interval delta t with the flow map associated to this parametric vector field of the position yij hat. For this dynamical system, we start with the same initial conditions as the training, as those in the training set, of course. So the idea is that if two dynamical systems, two vector fields have close trajectories, one to the other, then so will be the vector fields. So in order to optimize our weights and get a good approximation of f, we minimize the distance between the approximated trajectories, this yij hat, and the true ones, which are possibly noisy ones, but the only ones to which we that we have access to. So this yij. So this is simply the mean square error between the approximated trajectories, this yij hat, and the true ones. To minimize this, once we minimize this, we have a good approximation of our target vector field. So now I want to highlight how this can be seen in a very similar way to what you have in recurrent neural networks and in recurrent training for this kind of neural networks. Indeed, what you can think about is that the discrete flow map that you apply to the parametric model f theta, which I denote with the psi of theta delta t, is a map that you use to update the positions from a certain time to delta t seconds farther in the future, let's say. So you start with the initial condition, which is the same as those in the training set, and you update it with one application of this discrete flow map of the parametric model, and you get yi hat 1. Then, without injecting the information that you have from the training set, so without using any information of the intermediate snapshots, you just apply the same discrete flow map of the parametric vector field to yi1 hat, and you get yi hat 2, and you keep going up to the mth update. How you can use the training trajectories, the training snapshots, is simply to compute the loss function. So you inject this input signal at each stage of your update, and you increase the loss function, the loss value, by a new contribution. So you just compute the difference between the true position, yi1 in this case, and the approximated position with the parametric model, which is this yi1 hat. And you keep going up to the mth update, and this is just for one training initial condition, and then you need to do the same for any initial condition you have available. So You just sum the contributions resulting from all the training initial conditions. So this is why one can think of this approximation procedure as one of close by to the recurrent training in recurrent neural networks. And another thing that I want to highlight that is quite intuitive with this notation is that a quite different perspective to the same problem could be the one of, instead of approximating the vector field, approximating the flow map of the vector field. In that case, what would be our model, our network, if one wants to work with neural networks, is this one. So it's psi of theta delta t instead of f of theta x. So this would be the function that we want to train so that it matches the exact flow map of the target vector field. And this would make everything, instead of an inverse problem, a direct regression problem. In fact, you have access to direct measurements of this discrete flow map, which are these updates yi hat, which should match the true ones, which are yij. So this is just a parenthesis, and I will come back to this in the last part of the presentation. So now we can restrict the attention to Hamiltonian systems. In fact, up to now, we didn't care about conservative systems at all, because this learning framework in principle applies for generic dynamical systems, for generic vector fields. What changes with Hamiltonian systems, and in this case unconstrained ones, but it will be the same also for constrained ones, is that the vector field we are interested in as a particular structure. So one could choose either not to care about it, so just proceed as in a generic case, so just introduce a parametric model for f, so any vector valued function, like a neural network, for example, but it would be a loss of energies and of training procedures, let's say, in the sense that we know more about the system. We have some a priori information from the physical point of view of this dynamical system. And we know that it is fully described by a scalar function, which is the Hamiltonian energy. In fact, the Hamiltonian systems are described by the application of the symplectic matrix, DSJ, which is a skew-symmetric matrix, applied to the gradient of a Hamiltonian function, a certain scalar function, which goes from R2n to R. In fact, Hamiltonian systems are all defined on even dimensional spaces, so R2n. This turns out simply to be what is called the symplectic gradient, so the partial p derivative of h, where p is the second n set of n terms in the unknown x, and then we have the partial p derivative of h with the opposite sign, so minus this partial derivative. So since we have a quite synthetic model, fully summarized by h, we choose to approximate h with a certain parametric model. So we introduce a function h of theta, where theta is again a set of parameters that we want to train to fit to the particular case we are dealing with. And then our parametric model with the notation used before will simply be just j applied to this gradient of h of theta. Now, since we are dealing with unconstrained Hamiltonian systems, up to choosing a useful, a comfortable system of coordinates, one can suppose that the Hamiltonian is also separable, which means that it is made by two components, which are summed one with the other. One is called the kinetic energy of the system and the other the potential energy. And they both depend on different parts of the unknown. So the kinetic energy just depends on the conjugate momentum P of the variable Q. And instead the potential energy just depends on Q, so the configuration variable. Moreover, we also know that there is some structure, physical structure in this function. Indeed, we know that the kinetic energy should define a metric on R2n, should define a bilinear symmetric and positive definite form on R2N. And this is why we chose to exploit this information, this physical information, in the model that we adopt. So we modeled the first part, the kinetic energy, with a bilinear and symmetric positive semi-definite in general quadratic form, which is this one. So the weight that we will train here will be the matrix A. Then potentially one can even correct this to be to enforce the non-singularity of this matrix by adding a perturbation. But this is usually a matter of training the model and seeing if it is necessary to do that, or if it is naturally learned to be non-singular. While for the potential energy, many other choices can be done, but in principle, there's no prescribed structure of this part of the energy. So many different systems can be with completely different potential energies. And this is why here we choose to use a standard simple feed-forward neural network. And at least for the systems that we have considered, we used quite simple in the networks with few layers, usually 2 or 3, which are made by compositions of component-wise nonlinearities, usually hyperbolic tangents, and affine transformations of the inputs, so linear layers and nonlinear layers combined, nonlinear functions combined. So just to use the notation that we have introduced in this model, the weights, the parameters are theta that are made by the pair theta bar. So theta bar are the weights of the network. So now one can simply train this network, optimize this model to make it be close enough, sufficiently close to the trajectories of this target model, again, having access to a set of trajectory segments as in the general case. So, of course, when one trains a model, optimizes a model, is interested in measuring the quality of the approximation. So I want just to introduce 2 quantifiers of this quality of the approximation that we have used. The first one is just the most intuitive one. So it's exactly the loss function that we have used in the training, but this time it is applied to test trajectories. So on initial conditions on which the network has not been trained on, this xi bar. So what we do here is simply to take a set of initial conditions inside omega, which is the subset of R2N on which we want to infer something about the dynamics. And we take n bar of these initial conditions. We generate some discrete approximations of the trajectories associated to these initial conditions. We have that those without the hat are associated to the true model, so with the correct H, while those with the hat are associated to the trained parametric model. And we just measure the difference between the two and hope that they are close enough so that this is small enough as a quantity. One thing that I want to stress here is that since our purpose in the training is not to get a good approximation of the trajectories, but our purpose is to have a good approximation of the vector fields, we are not constrained to use the same training, the same numerical integrator that we have used in the training procedure in the test procedure. And this is why I'm using here a tilde on the psi, while we didn't have a tilde here in the training integrator. So in principle, they could be completely different integrators, because this is just used for the purpose of evaluating the quality of the training procedure. So in our experiments, this is usually the predefined implementation of ODE 4.5 with a quite strict tolerance. But the important thing is just that this and these are applied, are the same integrators, so that we don't introduce some bias due to the choice of the integrator in this evaluation of the quality. So this is the first quantifier, while the second is more based on the Hamiltonian function itself, and it is an average error on the Hamiltonian. So one thing that we need to recall here is that since the Hamiltonian dynamical systems are defined based on the gradient of the Hamiltonian function, if we add a scalar value to h, there's no impact on the dynamics. So there's no hope that our model learns exactly the same h, but the ideal setting would be that it learns h plus a certain constant c. So we don't want to penalize training procedures that just make h theta to differ from h by a constant, because this would be really the ideal case. This is why here we introduce we use this quantifier, which is actually the pointwise difference between the true Hamiltonian and the approximated model h theta. And we also remove here an average over these points on which we test the quality. And this average has the purpose to reduce, let's say, to quotient out this possibility of having h theta differing from h just by a constant. Indeed, this E2 would be 0 if h theta were just h plus a certain constant. So this is just to quotient out this possibility here. So now this is just a numerical experiment to make to get an idea of the quality of the approximation, and one can expect if the network, for example, is chosen accurately, so the number of layers and the hidden neurons are tailored to the specific problem, let's say, so the network is big enough. So we can get quite precise approximations of the trajectories, and then quite close approximations of the Hamiltonian function itself. This is a quite simple dynamical system on R4. It is chosen so that actually there is at least an interaction between the momenta P1 and P2. So this is not a diagonal term. And we made this just to make the problem a bit harder to work on, so a bit more challenging, and to see if this approach works still even on this example. And this is the potential energy of the system. So again, here I stressed the importance of detaching the choice of the integrator in the test phase from the one in the training phase. So now I just conclude the part on unconstrained Hamiltonian systems with one last part, which is on physics-informed regularization. So as mentioned at the beginning, we need to consider that in the if we want to propose a good solution to the problem of approximating dynamical systems, one sooner or later needs to care about the presence of noise in the training trajectories, because if a model is really effective, then it should be applied to real problems, and here the noise is inevitable. So one solution that we thought about, which is in the direction of imposing some structure to the learning framework, some physical structure, is to add some regularization term to the loss function, which is based on physics information that we have. This is just an instance of this idea, and the only one that we have tested also, but it's intuitively extensible also to other physical priors that one can have access to for the dynamics. So the idea is that if we don't just know that the dynamical system is Hamiltonian, so that the vector field is particularly structured, but we also know that there is, for example, an additional conserved quantity, so a first integral, this I, which is constant on the trajectories, then we can exploit this, adding this term here to the loss function. So penalizing models, penalizing parameters theta that make your approximated trajectories violate the conservation, violate too much the conservation of the conserved quantity I. So this should be conserved in the ideal setting. So we want to make this as close as possible to being conserved also by the approximated system. So this is just a loss function, a part of the loss function that we add. There is a penalization term gamma that needs to be adapted to the specific problem of interest, and we just penalize the difference between these updated positions. The value of I at the updated position at time j delta t from the value it has at the initial condition xi. So to conclude here, we have an example of this idea. This is on a dynamical system on R4. This is actually a completely integrable system. It has 2 parts in the Hamiltonian, and these 2 parts are based on different parts of the unknown x. So they are not interacting, this Q1, P1 with Q2, P2. And this makes both H1 and H2 conserved quantities of the system. So we set here I to be equal H1, and we inject some noise in the training trajectories. And we do that setting this delta ij to be epsilon nij, where nij is being distributed normally as a normal 0, 1. And here we have that we are testing the quality of our approximation on clean trajectories, of course, because we don't want to overfit the noisy trajectories, but ideally our training, even if it is based on noisy trajectories, should perform well on the clean ones. So this is the metric, the quantifier E1 that we have introduced before. And it measures simply the discrepancy from predicted and clean true trajectories. So we see that with a regularization added of this kind, in this experiment, gamma is of the 10 minus 3, power minus 3, and we see an improvement here. So it's very much problem dependent, this regularization term, but one should keep in mind that exploiting some information should be possible either in a soft way, so adding some regularization, or even it should be interesting to test hard constraints in the network architecture, so more imposed at the level of the model than at a soft level like here. Others could be symmetries in the potential energy, equivariances with respect to some group actions, and so on. So this is everything to be tested and to be understood a bit better for sure. So now we can move to constrained Hamiltonian systems. And here I want to start discussing a bit the model that we choose, not at the level of approximation, but at the level of characterizing the dynamics of constrained Hamiltonian systems. Indeed, there's no unique sorry, I don't know what happened. Okay, so there's no unique choice here, but there is for sure one intuitive starting point, which is a differential algebraic equation. So I want to first punctualize here that we work with holonomically constrained Hamiltonian systems, so we don't deal with constraints on the momenta or on the velocities, and these constraints are also time independent. So this is another important thing. It's for sure interesting to extend this or with this approach or something similar to more generic problems like non-holonomic systems, but we didn't focus on them in this work. So the starting point is to add to the ODEs we had before this x dot equal j applied to the gradient of the Hamiltonian function h, with x being split into q and p. We have a certain set of constraints on the configuration variable q. The constraints are usually characterized by a certain function, vector values function, which goes from Rn into Rn. So m is the number of the constraints. What we suppose here is that there's no that all the components of G are fundamental in the sense that they are functionally independent, which means that the constraint space has a dimensionality which is n minus m, so which is the codimension. So it has codimension m. So this allows us to say that at least the configurations Q need to evolve on a certain space, which is a submanifold of Rn, and it is made by the vectors Q in Rn that satisfy the constraint G of Q equals 0. So this is for sure true. But actually, there is some hidden constraint when one imposes this kind of structure on the system. And it is called hidden, this constraint, because while this is a physical constraint that we impose, for example, for a spherical pendulum or even a simple pendulum, it is the length of the pendulum, of the rods. This is a physical constraint, while this induces some hidden constraint also on the other variable p. And similarly, if one uses the Lagrangian formulation of the same dynamical system, it will translate into a constraint on the velocity q dot or v. So this is a constraint that one can get differentiating with respect to time, this constraint equation. So this is a total time derivative where q is intended to be a solution of our ODE, hence. So differentiating with respect to time here, we get by chain rule the Jacobian of G, which I call big G of Q, applied to the time derivative of Q. But since Q is meant to be the a solution, a component, a part of the solution of this ODE, then we know that by construction of Hamiltonian systems, this translates into G of Q applied to the partial p derivative of H. So we now see that this constraint, which is physical, imposes some constraints also on P, even if it is just holonomic, so it's just a configuration constraint. This makes us understand now that actually the dynamics is not just constrained to evolve here, but on a lifted set of constraints that translates from the differential geometric point of view into the cotangent bundle of Q. So the manifold in which everything is evolving, as long as we start with a compatible set of initial conditions, is this M, which is the cotangent bundle of Q. The cotangent bundle of Q is simply characterized by the physical constraint G of Q and this hidden constraint that we have just derived. So the space where we will work on is the set of QP in R2M, so that G of Q equals 0 and this quantity is equal 0. Since we have supposed the components of G being functionally independent, this will be a manifold of codimension 2m. So in particular, it will have dimension 2 times n minus m. So the idea now is that since we would like to get a formulation of this dynamical system, which is with some differential geometric background and understanding, we would like to translate this differential algebraic equation into a vector field on this manifold M. This can be done in many different ways, and in many applications, usually in engineering applications, this is done using Lagrange multipliers, and this is for sure an option, and there are already works, at least once, one by Finzi and co-authors, in which this is the approach utilized to approximate dynamical systems, constrained Hamiltonian systems on of this kind, let's say. But we wanted to test a different approach, which was more based on a differential geometric understanding of the problem. So now we will see how we can do that. So I omitted the full derivation because it's not not fundamental for the understanding of the data-driven approach to this kind of problems. But you can find the details in many books and other works. In case I can just suggest them later if you want. So the idea now is that we have a quite specific geometric framework here. So we have a configuration space, which is a manifold of dimension m, n minus m, sorry. It is made by the q's in Rn so that g of q is 0, so that they satisfy the physical constraint. Then there is another important space with dynamical systems evolving on manifolds, which is the tangent space to this manifold q. And this will be the space where the derivative of curves on q evolve and live, actually. And it is made by the v's in Rn, in this case, that live in the kernel space of g of q. And this can be simply seen by the calculation that we have done before. Indeed, if g of q is 0, which is equivalent to say that t that maps into q of t is a curve in the manifold q, then its derivative will satisfy g of q times q dot equals 0. So we can fully characterize the tangent space at q to the manifold q in this way here. And this is sufficient in order to derive a set of ODEs, so without any kind of constraints, that fully characterize the model of interest. And we can do that thanks to an orthogonal projection. The orthogonal projection is this one, and it projects on the tangent space at q of the manifold q. So essentially on the kernel of the Jacobian of the constraint function. So this is a function that goes from Rn into the tangent space at q to q, and it's applied linearly to the inputs. It goes from v into p of q applied to v. So just to get an intuition of how one can derive the equations that we can see here, it's not too important, the explicit expression here, but the intuition is simply that one can proceed as in the derivation of unconstrained Hamilton's equations or Euler-Lagrange equations. But instead of unconstraining the variations of the curves to get the action principle satisfied and hence the equations of we're interested in, one just needs to project these variations on the right space. And this can be done with this projection matrix P of Q. So now we can see that we can transform a set of differential algebraic equations defined on R2n, which is this one, which is a bit trickier to be tackled numerically because there are many strategies, numerical strategies to deal with this set of ODEs and algebraic equations, but we wanted to reframe the problem in a very similar way to the unconstrained case that we have seen before. So we wanted a vector field on a nonlinear space. So we transformed in this way the differential algebraic equation onto an ODE on a nonlinear space, which is smaller dimensional. So this is the M manifold here. And we can see that even here, the dynamics is fully described by two components that are playing together. One is the geometry of the system, which is encoded in P. And actually, I didn't write the expression of this because it's quite long, but the important thing is that this is just involving P of Q, Q, and P. So it's nothing related to H. It's fully characterized once one fixes G of Q. And this is the geometric part playing here. And then there is the dynamical part. So once you have fixed the manifold, the constraints, you can introduce there a certain dynamical system. And this can be done introducing a certain Hamiltonian energy. And this is what is coming here, here, and here. So we see that here we get something similar to the unconstrained formulation. But of course, there is some interaction between the partial derivatives with respect to P and Q, which is due to the nonlinearity of the space. This is, for example, this term here that is not present at all in the unconstrained case. And then since we are dealing not with a system on R2n, but on a smaller dimensional space, we need to project the derivatives on the right space. And this is why these two projection maps appear here. So now we are well, I forgot about this, but I've chosen to make it a bit clearer, just showing an example. So everything we have seen in the previous slide can be specialized for specific manifolds, of course. And with the particular case of the unit sphere of R3, one gets a quite simpler formulation. So the unit sphere can be described in this way. So it's the set of Qs in R3 that have Euclidean norm equal 1. So this is a submanifold of dimension 3 minus 1, because we just have one constraint, so 2. And the tangent space here can be obtained as the kernel of this function here. And it is again, it is hence just the set of orthogonal vectors to Q. So that Q transpose B is equal 0. The projection even takes a quite simple form, and it is this one here. So it's the identity minus the outer product between Q and itself applied to V. So one can test that if you multiply this by Q transpose, you get 0. So this is orthogonal. So it is projected on the right space. And introducing the right expressions specific for the sphere, one can recover the ODEs for any dynamical system that is constrained on spheres, where what changes is, of course, the Hamiltonian, because if one wants a particular dynamics, it needs to change H. So we can see that the expression is not too complicated, and once the geometry is fixed, everything is given up to the Hamiltonian, which is whatever function you want, as long as it goes from R6 in this case into R. So one thing that maybe I didn't stress enough is that the advantage of this approach and also of the Lagrange multipliers one is that we are working with the ambient space coordinates. So we are dealing with Hamiltonians, which are usually simpler than those you would get with when you work with local coordinates on manifolds, because usually the Hamiltonian is dealing with less interactions between the components of the unknown. And hence, this is favorable if one wants to approximate the Hamiltonian itself, because the learning problem should become a bit easier. So now we are ready to pass to the learning problem. So working exactly as in the generic case we have seen at the beginning, we have again a certain target vector field, which is F that we had before. So this is the vector field we are interested in, the right-hand side of the ODE. And hence, we just need to introduce a model that ideally should compare to this target vector field. So what changes with respect to the generic case is that it is structured as a vector field. So as for the unconstrained case, one can just model the Hamiltonian function. So we see that here we are able to to reframe a constrained problem, which in principle could be described with a differential algebraic equation exactly in the same way as one would do for unconstrained problems, because we have a vector field on a nonlinear manifold. So we again introduce a model for the Hamiltonian function, and we do that in a parametric way as for the unconstrained case. So we have h theta of QP, which is made by a part, which is the kinetic energy, and the part, which is the potential energy. So what changes here is nothing in the potential energy, because we still have a feed-forward neural network. What changes is that, in principle, in general, these kind of Hamiltonians are not separable. There is a dependency on the configuration variable Q due to the nonlinearity of the manifold on which we are working on. So this is why here we have a m theta 1 minus 1 of Q, because this is possibly a variable, a matrix valued function. it is still positive semi-definite as a bilinear form, but it is usually Q-dependent. So one needs here to try different strategies to model this matrix, but in general, the dependency that one has from Q is given once the geometry is fixed. So usually one can recover this model, this matrix here, when it is known the geometry and it is given a certain constant matrix, which is similar to the mass matrix we had at the beginning. So, for example, in the spherical pendulum, we model this with a pre-multiplication and post-multiplication by a certain function of Q, which is given, and an SPD constant matrix, that is the one we learn as for the unconstrained case. So here we have, again, a set of parameters, theta, which are theta 1, theta 2, that are modeling the mass matrix and the feed-forward network. So before moving on, I want to stress one thing, which is what allows us to think about one question in the last part of the presentation, which is that this vector field, even if it is well-defined as a vector field on M, makes completely sense also for points outside of M. So since we are framing everything as using ambient space coordinates, everything is well-defined also for points in R2n minus M in principle. So one could be interested, and this is what we tried to investigate with some experiments, in understanding if preserving M in the training is really important or not, or more precisely, when it can be important and when it is not that fundamental. So this is just an example. You can find this in the paper, and it is just to get an idea of how one can get the predictions, so how accurate they can be. So this is the case of the double spherical pendulum. And here we have the plot of the first configuration variable Q1 and the second Q2. And you see in black the trajectories corresponding to the true Hamiltonian, and in red those for the predicted one. And in this case, they overlap quite well. So the mean square error between test trajectories here is of the order of 10 minus 6. So it's quite accurate as a prediction. Of course, if you increase the dimensionality of the problem from 12, like in this case, to higher dimensional spaces, one needs to care more about the network. We tried, for example, with 6 or 7 connected pendula, and you need to play quite a lot with the network in order to get satisfying results, but the framework applies for all these kind of systems. So now we can move to the last part of the presentation, which is trying to answer to a specific question, which is how one should design the integrator used in the training. Because in principle, one can choose the integrator in any different way one prefers. But we know that there is a whole field of numerical analysis, which is geometric integration. And this is made by a huge family of integrators designed to preserve some structure. So here we want to see if preserving the geometry M is important here or not. So one thing that I want to say first is that going back to this slide, as I said at the beginning, if one thinks to this learning problem not as a learning problem for the vector field, for the Hamiltonian, but as an approximation problem for the flow map, then it's probably not even in discussion if one should preserve the geometry or not. Because if this should be an approximation of the exact flow map of a vector field whose trajectories are leading on this nonlinear manifold M, then there's probably not much interest in not reproducing this property in our model. So In that case, it would be fundamental, at least for my understanding, to preserve this structure. But if one is interested, like what we are discussing here, in approximating the vector field and not the flow map, then it's not that clear if the preservation of M is important. Because as I've said here, the vector field and the model all make sense also outside of M. And the Hamiltonian function is well defined also for points outside M. So in principle, there's no clear reason why one should preserve this M. So I tried just to highlight some pros and cons of doing that. So starting with the pros, we have that on the manifold M, the Hamiltonian function h theta and also h is unique. In fact, I want to recall that here we are always working with projection maps, and projection maps on lower dimensional spaces. So these are non-trivial kernels. So if we add here, so if this partial p derivative has some terms, some contributions which project on the 0 point on the manifold, then there's no impact of this perturbation on the dynamics. So outside of the manifold, in principle, the Hamiltonian is not unique because you still get the same dynamics on the manifold, even if you change it in a proper way. So by preserving the manifold, for sure, we are promoting the learning of the exact function h because it is unique there, up to a constant, of course. Then there is another pair of motivations that, for me, it is what moved us in trying to understand better this question, which is that if you have a set of training trajectories that correspond to the true ones of the target dynamical system, you know that those live on the manifold M. So you know that also the simulated ones should live there. So if you preserve the manifold also in the training, you at least remove one contribution to the error, to the discrepancy between the predicted trajectories and the training one and the true ones, because you're not introducing some drift from the manifold, which contributes to this difference here. So in principle, you should help the training procedure in this way. However, there are other cons. There are some cons in this approach, in the one of preserving the manifold M. And for sure, these kind of methods usually are more involved in the expression. The way in which the vector field is entering into the integrator usually is more involved. And oftentimes they are even implicit. So this again, connecting to the second cons, this can make the loss function harder to be optimized. So you can get something more physically interpretable, but maybe you can get poorer approximations because you're not able to optimize that well the loss function. So this is something to consider. And then in general, there is also another problem, which is that the integrator is just one piece of the full training framework and procedure. So it's not that direct that if you use a better integrator, in some sense, you get better approximation qualities, where this sense is in terms of preserving the geometry. So we just try to understand this question, and to do that, removing one of the problems, which is the one of having to deal with implicit integrators, we restrict it to the case of homogeneous manifolds. So just a brief summary of what is a homogeneous manifold. So it is a manifold that admits a certain Lie group G that is acting transitively on it, where it's, I'm not sure what is the background of everyone here. So just to get an intuition, a group action is simply a function that maps a pair of inputs G and M1, where G is in the Lie group G and M1 of the manifold, into another point of the manifold, which is M2. The fact that this action is transitive means that you can pass from any point M1 into any other point M2, thanks to some group element G. So there is always some solution G in G of this equation here, if one wants to think about this in that way. So this is the geometric understanding, let's say. So why should we care about homogeneous manifolds? Well, because here at least there is a class of methods, numerical methods, that allow you to preserve the geometry using an explicit integrator. And these are Lie group methods. So the idea is that if you have this kind of structure, geometric structure, you're able to locally transfer the vector field, the dynamics, on a simpler space, which is linear, where you can use any numerical method, like Runge-Kutta method or for the whatever you want, and then you're able to get some information on how to move the point M1, the starting point, into another point M2, which is sufficiently close to the right update if you follow the integral curves of the dynamical system on the manifold. But I've tried to make some visualization of this in the next slide, so just to get an idea. And the simplest of these numerical methods is the Lie-Euler method, which is updating the positions in this way. So if you start at a certain time in the position Yij, you will update it into the position Yij plus 1, thanks to the Lie group action var phi. So this one, which is transitive because you know that the manifold is homogeneous. And the way in which you update this point here is thanks to this exponential here. The exponential usually for the Lie groups that we are using is just the matrix exponential with some properly defined matrix space. So for example, if you work with spheres, you can think of these terms here as Q-symmetric matrices that Lie, because the Lie algebra of the group that acts on S2 in a transitive way, which is the one of rotation matrices, is just a space of skew-symmetric matrices. So you would have that this is a point in the sphere, S2. This is a skew-symmetric matrix. The exponential of a skew-symmetric matrix is also always a rotation matrix. And this action is simply the matrix multiplied with a vector. And this will preserve the norm of the vector, so will preserve the fact that it belongs to the sphere. So you have a quite simple way to construct a method that preserves the manifold, the geometry. So the idea is that we wanted to remove one of the complications of using constraint preserving methods, which is the implicitness. And we used thence Lie group methods here. So I just have a brief graphical understanding of this, but I don't plan to go into details here. It's simply that these Lie group methods, or at least a class of Lie group methods, lifts the dynamics on a simpler space, which is the algebra G. And this is done thanks to some function psi. And the updated position on the algebra is then projected on the group G thanks to the exponential map. The exponential map is not the unique choice. There are other options like the Cayley map, for example, if you're dealing with SO3, but there are many other options in general. And then you want to use this computed point in the group to update your position thanks to the action. So this is how we update the position and get the numerical approximations of the trajectories. So now that I've introduced this, I'm ready to go to the last part. So 2 numerical experiments. In the first one, we see a case in which preserving the geometry helps in the quality of the approximation. And in the second, we see some an instance in which there's not much influence, and actually we get quite close results using a method of this kind that preserves the geometry and a classical group method, a classical Runge-Kutta method of the same order. So this is the first case in which preserving the geometry, where by geometry I mean the manifold M, helps. And this is quite a simple case, but it suggests a class of problems in which it is actually reasonable to preserve the structure, the geometric structure of the problem. So suppose that you don't just know that the system is Hamiltonian and it is constrained, but you also have much more information about the structure of the Hamiltonian. So you know, for example, in the spherical pendulum that the mass matrix is diagonal, so you just need to learn a scalar a rescaling of the identity matrix, so it is just of this form, the kinetic energy, and you know that the potential is of this form. It's quite simple as an example, but it helps understanding when preserving the geometry is important. So, of course, if one has this much understanding, this much knowledge about the system, it is desirable to get a very precise approximation of this U and this mass M. Otherwise, we would have a very poor model. So here we have done this experiment for the spherical pendulum, and we have done that in two different settings. One, which is using a Runge-Kutta method of order 4 in the training procedure, which is not preserving the constraint M at all. It's just integrating the dynamical system we have, which is in the continuous time setting on the right manifold, but once you discretize it, you won't preserve the manifold. And we compare this with a commutator-free method of order 4, which is just a Lie group method, again, of order 4, but so it will preserve the right space M. So here I reported the two metrics, E1 and E2, that I introduced before. And just to make the quantities here clear, all these experiments are done fixing the double precision for the experiments, otherwise preserving to machine accuracy, the manifold M wouldn't make sense if the zero term is 10⁻8. So we add this setting in the training, and we see two orders of magnitudes of difference in the E1 metric, in this case, using a constraint preserving method. And here, one order of magnitude of difference between the two methods on the E2 metric, where I recall that E1 is the mean square error between test trajectories, and E2 is the average error on the Hamiltonian. So we see a better result if you preserve the structure when you have much understanding, much knowledge on the Hamiltonian expression, let's say. And now we can move to the other case, which is again done for the same example, the same mechanical system, which is the spherical pendulum. So we have, again, n equal 3, so it's a dynamical system on R6. We have that the training is done with trajectories that are trajectory segments with 3 points and a final time, integration time of 0.1. And we have 500 training initial conditions. So here we again compare Runge-Kutta 4 and commutator free of order 4. And we see that if we don't suppose any knowledge on the expression of the Hamiltonian, so if we don't do like here, if we don't suppose it to be like this, the kinetic energy and linear potential energy, but we just model as a generic feed-forward network the potential energy, and as generic bilinear for the kinetic one, we don't get any difference, essentially, if you preserve the manifold or not. This is quite interesting because if you use constraint preserving methods, as we have seen in the cons part in the previous slide, you need to deal with higher computational times and efforts, because you have to work with the exponential of matrices, and you have more involved integrators. And at least for us, it was quite surprising to notice a comparable performance. But actually, the understanding that we are getting of this situation here is that, as always with neural networks and machine learning, what you are aiming for is not actually a global minimum of your loss function, but you're hoping for a good enough local minimum. So you're never getting a zero loss value. You're getting something close to zero, and hence the relevance of preserving to machine accuracy the manifold M in the training procedure is not necessarily that impactful, because what is more relevant is, for example, as we have noticed experimentally, the order of the methods. We have seen, for example, that passing from a method of order 1 to a method of order 4, even if it is not constraint preserving, then you get much more improvements in the results. But keeping the same order in the method and just changing the structure preservation of property of these methods does not seem to be that impactful, because probably one has to get much more precise results in the approximation of the in the values of the loss function in order to appreciate the importance of this structure preservation. So here, of course, one can experiment in many different ways. For example, starting the training with some integrator and then proceeding for the remaining epochs with another. So moving close to a good global local minimum with one integrator, and then refining the approximation with another. But even other properties can be of interest, like symplecticity or symmetry, the symmetric property of integrators. But in this work, we wanted just to isolate the geometry of the system and see how relevant it is. While if you use symmetric or symplectic methods like shake and rattle, you are not able to isolate just the geometry, because you get much more properties that are preserved, and you're not necessarily understanding what is really playing a huge role in the quality of the approximation and what is not. So this was our choice in this work here. And with this, I want to thank you for the attention, and for me, it's everything. You can find the slides here if you want.
All right, thank you very much. Thank you. So there is the question on the chat. Do you want to ask it, Thomas Dendorfet? Okay. Yeah, we can't hear you. Yeah.
Can you hear me now?
Yes.
Yes.
Yeah, okay, sorry. Yeah, thank you very much for the really nice talk. I just wanted to ask a question, if I may, for when I think it was on slide 15 or 14, when you noted that the system is defined also outside the manifold.
Yes.
Yeah, okay. Or 13 here. Yes, 13. Yeah, but isn't so for this f hat function, the projection P of Q in general depends on the configuration space, so on the Q manifold, right?
Yeah,
or
sure.
do I misunderstand something here?
No. You understood correctly, and I was a bit imprecise here, in the sense that h of theta is well defined even outside, and for a quite huge class of mechanical systems, you can characterize this projection map so that it is flexible to the level set that you are using of the G function. For example, the norm is of Q is preserved, but is equal to a constant, but you can change the constant. So here you can just quotient with respect to the norm squared of Q, and you will get a projection on the sphere of norm fixed norm, but not necessarily one. So yes, you're right, completely right. I need to fix this.
Thank you.
Thank you.
Hello, I have a question.
Yes.
So thank you very much for the talk. I just want to first, I want to ask, because I saw a lot of works that they all assume this separable Hamiltonian. So I just wonder why it is so important to assume this. Is this does it still work without this assumption?
Okay, in principle, it's not really fundamental to use separability of the Hamiltonian. The reason why it is oftentimes imposed or supposed is because if you want to use symplectic integrators, then there are integrators of this kind that are explicit if applied to separable Hamiltonian systems. So you can get an easier structure of the network if you have a separable Hamiltonian. But in principle, you can have any function here.
I see, because of the explicitness of symplectic integrators, right?
Yeah.
I see this.
Yeah, I would be really interested in seeing how one can work with implicit integrators, because this opens a lot of options in structure preserving methods, like symplectic methods for constrained systems or symmetric ones. And I've seen just some works in which it is done, and it is not too complicated as an idea, with just one time step, so with m equal 1 here, because in that case it's just a term that you include in the loss function, which minimizes the residual between the left and the right hand side of the ODE. But with multiple time steps, I still have to find at least how one can do that. Probably there are works on.
Yeah. Thank you. So I have another question. So you mentioned a lot of applications of projection maps when you try to approximate the vector fields, right? But you mentioned later that this approach doesn't guarantee that this trajectory are still on the constrained manifold. So I'm just curious if you talk about the projection, so they already makes it on the configuration space that you want, but why we don't impose it to make sure that the trajectory is still on the manifold? I mean, we already use this projection, but only for the approximation of vector fields, but not make sure the trajectory are on the manifold.
Yeah, so I said that this projection makes this as a vector field on a properly defined vector field on M. And also the continuous in time solution, because of this structure, evolves on the right manifold. But the problem with, maybe I didn't understand correctly the question, but in case I can just try to what I understood. So if you start on a manifold, a nonlinear space at a certain point, the sphere, and you do one step of any numerical method, you necessarily drift away from the manifold. So you get outside of the manifold, not too much. It depends on the accuracy of the method. If it is of order p and you do a time step which is long h, the drift will be of the order of h power p plus 1. So it's quite neglectable in general, but it depends on what you're interested in. So even if the vector field is of this kind, you would drift out of the manifold. But maybe I didn't get the question.
Yeah, so my question is simply I understand what you're talking about. Just I'm curious why this application of projection still cannot make trajectories themselves on the manifold, just for a better approximation for the vector field. Yeah.
Okay. So you would project the trajectories themselves?
Yeah, I mean, it sounds to me like more natural because we already use the projection. But finally impose is,
this is a projection on the tangent space. so not on the manifold. So,
yeah. I see.
so it would be for sure possible. There are numerical methods that are projection methods, and you do just one unconstrained step, like any classical method, and then you project back, and you lose most of the properties that you had in the unconstrained step, but you can do that. Yes, this would be for sure simpler in the structure than a Regroup method.
Yeah, I saw your Regroup method is exactly preserving the trajectories on the manifold. Yeah. So that's why I raised this question. Thanks.
Yeah, this is why for us it was a bit surprising actually that we didn't get better results preserving the manifold. But the explanation that I gave before is what we arrived at.
Yeah, it's for sure much harder than, yeah. Thanks for your answer.
Thank you for the question.
Hello, Dr. Murari. My name is Zhi Junqiao from United States. May I ask you a simple question?
Sure.
Yeah, thank you. This is a very interesting talk. So my personally doing integrable systems, actually I typed a question on the chat. My question is for the constrained Hamiltonian system. Is that completely integrable in the sense of a Liouville?
Yeah, it would be interesting. I think this is not.
Oh, no, okay. Yeah,
But,
can zoom me back, right, that slide. The constraint system.
Yeah,
I want to know the constraint. What is your constraint?
For the spherical pendulum or chain of spherical pendula, it is this constraint here.
Oh, that actually is like a sphere.
Yeah, this is a sphere. So this was the example.
Yeah, that is a sphere.
Yeah.
If a constraint on a sphere, there's another well-known constraint is called Neumann. I don't know you know the Neumann constraint.
No.
So usually for finite Neumann constraint. Neumann constraint, that's exactly the usually Hamiltonian system is restricted to the sphere. Then this typically is called Neumann constraint in the integrable system theory. So you do have a TQ, T sub Q, capital Q. That's actually a tangent space, right?
Mm.
Yeah, the next equation, capital T sub Q, the capital Q equals the V. Yeah, right.
The tangent space.
This is actually a tangent space.
Yeah.
Oh, that's very interesting. If that is connected to the Neumann system, this should be integrable. I will study that for detail.
Okay.
If you have the paper published, this is a very good structure because you guys applied this scheme to the numerical simulation for deep learning or machine learning. That's fantastic.
We work with this and chains of, and we worked with this constraint and Cartesian products of S2, so chains of pendula connected. And just thinking about this is a system on a 4-dimensional space for the single pendulum.
Yeah, doesn't matter what dimension. It really doesn't matter. In mathematics, any even dimensions.
Yeah, sure. But I was trying to think about the complete integrability because we have one conserved quantity, which is h, but I don't think there is another first integral.
Right, that's my major question asked that you highlight in red. That is integrable or not, you don't know yet, right?
No, because what we would need here, if you want Liouville integrability, is another first integral, right?
Correct.
And immediately I cannot find one, but it's quite a regular system. If you pass to double pendula, it's chaotic and maybe it's not too.
So what is your W? What is capital W here?
W is, I cannot recall the expression explicitly, but it's a term which is involving three terms that are based on P of Q multiplied with P and with Q. So I have it in the paper, but it's just something that completely depends on the geometry. So nothing on
I
it.
see. Okay. Is it related to noisy, something like that?
Here we didn't work with noise, but in the reviewed version that we will update in some weeks, we have just received the referee comments.
Okay.
We want to add something on noisy trajectories here.
Okay.
And so how was it called? Neumann systems, you said?
Neumann system exactly, you know, see here, you put down the capital Q. Right now is, oh, you put a little g, the earlier one, you put the capital Q, you're right.
Yeah.
This is exactly a sphere.
Yeah.
It's usually a Hamiltonian system is restricted to the sphere. You know, that's, you know, so one of a condition. The other condition, exactly second one, is you catching the space Q, yes.
Yeah, this condition is a natural one coming from this. Right?
Yes, combined together, that is called a Neumann condition, basically. That's what usually in the theory of an integral system, we call the Neumann system. But first of all, you already have a Hamiltonian.
Yeah, yeah.
Okay, David, if you have the paper published on the archive, maybe I check there. I'm gonna communicate with you more details.
Yeah, there is a preprint available. I don't know if I should.
Okay.
Maybe you can just find it. It's called like this. This is the title.
Okay, great, great. Thank you so much. I will contact you later. Yeah.
Oh, thank you for the integrability question.
Yeah, this is really, really interesting. Great talk. Great job.
I studied integrability for the master thesis, so it's a problem that I'm interested in.
Okay, great, great. Okay. See you. Bye-bye.
Bye.
All right, thank you very much. Thank you. Any other questions or comments?
Hello, this is Tom Bertolin. Unfortunately, the Gradanis paper, which I see you did cite in the archive, it was very similar to one that we did at almost exactly the same time. But I think theirs is, it's everyone Googles it instead. It's very sad.
Hey,
I have one question. So I guess the constraints and then the simplicity are two things to impose are kind of separate. So I guess, is it possible to elide the constraints if you like pose a system just in minimal coordinates, like just Euler angles, even for the spherical pendulum?
Yeah, this would be a completely different approach, but for sure interesting. So in that case, you would have less degrees of freedom for sure. But the appealing part of using ambient space coordinates, whatever the approach you use, either this one that we have here, which is based on projections, or the one of Lagrange multipliers, is that if you use these ambient space coordinates, usually the expression of the Hamiltonian is a bit less involved. So even the potential energy takes a simpler form, and hence it's simpler to learn. But yeah, for sure with intrinsic coordinates, it would be very interesting to understand how the network behaves. And even in the starting paper by Gredanus and co-authors, they studied the simple pendulum, I think.
Yeah.
So they used the angle coordinate. So in that case, of course, there is quite simple, the expression, but
so you can also do ambient coordinates in the
yeah, you could use X and Y, right? And
just to make your life a little bit harder in one sense and easier in another.
Yeah, from on one side, it seems harder because you're introducing more variables, for sure. But on the other, the expression is a bit simpler. Maybe not with the simple pendulum, but if you even have a the spherical pendulum, a couple of these pendula connected, or even the simple pendula, double pendula, it gets a bit more involved, the interaction between the intrinsic coordinates, right?
Right, like I'm interested recently in modeling linked rigid bodies, like chains. And here, like the forces involved, it makes most sense to describe them in ambient coordinates. But of course, it's a lot easier to describe the constraint system in minimal coordinates.
Yeah, sure. Sure, it's more interesting maybe from a differential geometric point of view, because you have a vector field on the manifolds, but it's a bit difficult to tackle the joints, the interactions between the masses, and yeah.
Well, thanks. I will read the draft. Please include us as well. I think they have like 380 citations, and we have just 61. And it's like the same time, the same paper.
Okay, yeah, I took down the links, and I will take a look at them for sure. Thank you.
Thank you.
All right, thank you very much. Thank you. Other questions or comments? Okay, thank you, David. It's very nice talk.
No problem. Thank you very much for the invitation again.
Okay, thanks. Bye-bye. Bye.
Bye.